in this video we're going to talk a little bit more about Gibbs free energy and Helmholtz free energy, how we can get Gibbs free energy for a chemical reaction, and Helmholtz free energy is a very similar way, and talk about then how Gibbs and Helmholtz free energies are related with work. Okay. So to get the standard molar Gibbs energy change for a chemical reaction, we got two different ways we can do this. If we calculate, right, the enthalpy change for our reaction and the entropy change for our reaction, right? And I can just use delta G equals delta H minus T delta S, okay? Right? If I know what delta H and delta S are, very straightforward way to get delta G for a chemical reaction, right? Because again, a chemical reaction is done under constant temperature pressure conditions, and so this relationship holds, okay? Temperature's changing, this equation doesn't really work very well, okay? Now, another way to get this is if I know the Gibbs free energy of formation of my reactants and products, then I can use that same type of formula where I do the products minus reactants multiplied by stoichiometric coefficients to get the Gibbs free energy change for my chemical reaction. Okay, right? Notice that standard molar Gibbs free energy changes for pure elements and their standard states are defined as zero, just like enthalpy. Okay, and we need to do this for Gibbs free energy because Gibbs free energy is related with terms like enthalpy, which doesn't have a predefined value. Okay, and so right, these delta GFs are again Gibbs free energy changes for formation reactions, and formation reactions for pure elements and their standard states is not a reaction, right? And so its Gibbs free energy change is going to be zero, right? Okay. Now, right, if I want to know how much maximum work I can do on the surroundings, okay, this is going to be related with the Clausius inequality. Okay, and so, right, we're going to start with that Clausius inequality, okay, and we're going to, right, multiply everything by temperature to get TdS is greater than or equal to dQ. Okay. Right, I'm then going to use the first law of thermodynamics, du equals dW plus dQ, right, and plug that in for dQ, right, or plug in, sorry, for dQ what TdS is, right, to get that du is always less than or equal to dW plus TdS, okay. So again, to get this, I just take this guy here, okay, and I plug in TdS for dQ, okay, to get this inequality, right? I'm going to rearrange the inequality, right, to write that dW is greater than or equal to du minus TdS, okay? And now recall for constant temperature, du minus TdS is just dW or dA, okay? And then if we multiply everything by -1, okay, right, then minus dW is dW of the surroundings, okay? And so we get the dW of the surroundings is less than or equal to minus dA, okay? Which is telling us that the change in Helmholtz free energy times -1, so the negative Helmholtz free energy change is equal to the maximum amount of work that the surroundings, that can be done on the surroundings, okay? Right, so again, we see here that dW surroundings is less than or equal to dA, right? So that's telling us that the work done by the surroundings, right, right, is always less than or equal to this Helmholtz free energy. So the Helmholtz free energy gives us a maximum amount of work that can be done, okay, on the surroundings, okay. All right, and this is expansion compression work, okay. Now let's look at non-expansion work, right? So starting here with the definition of enthalpy, right? The total differential that is given there, right? And then in here, if I substitute in the first law of thermodynamics for du, okay, right? And I break up my work into expansion work and non-expansion work, right? That's what the E is there for extra work, okay? If I assume a reversible change, right, I get dW expansion reversibles, right, just minus PdV, okay, because P external is equal to P for a reversible process, okay? And dq reversible is equal to TdS. Okay, so substituting those in, right, into equation 3, we get dH equals TdS minus PV dV plus dWe reversible, right, the extra reversible work. Okay. Right, plus PdV plus PdP, and simplify those things by getting rid of the PdVs, okay? Right, we're left with this. Right, I'm just rewriting again from the last slide that dH reversible equals TdS plus dW, extra work reversible plus VdP, okay? Now, since H is a state function, dH is reversible is equal to dH, okay? We're going to use the definition of G, okay, to have dG equals dH minus TdS minus SDT. Substituting in dH from up above into the equation given here, we get that dG equals TdS minus the extra work plus VdP minus TdS minus SDT, right? So you see the TdS terms cancel, and I'm left with VdP minus SDT plus that extra work. Okay. Well, right, we've assumed this is a constant temperature pressure system, right? So dt is equal to 0 and dP is equal to 0. Okay, so these two terms are just 0. So that leaves us with dg is just equal to dW extra reversible. Okay, or take the negative of those, gives us that minus dg is equal to dW extra reversible for the surroundings. Okay. And so what that relates to is then that minus delta G is equal to the maximum amount of non-expansion work that can be done by a system on the surroundings, okay? Assuming constant temperature pressure conditions, okay? So, this is how one can calculate the maximum amount of, charge or electricity or power you can get from a battery, right? If you know the free energy change for the chemical reactions that take the electrochemical reactions in your battery, then you can use that to calculate what is the maximum amount of electrical work I can get from that battery, okay? Right? Same with chemical work or things like that in your system with enzymes or other things like that, right? So using this free energy to give you the maximum potential work that can be done is always a decent thing to do, okay, for a lot of problems, okay? So it's a good limit to know and understand, so you know how much work you might be able to get out for a given process, okay? All right, and so that's it for this video on Helmholtz and Gibbs free energy and their relationships between maximum amount of expansion work and maximum amount of non-expansion work.